This is chapter 3. In this chapter, you will learn about real vector spaces. First, let us see some standard sets of real numbers. You may already be familiar with these, but a revision is important. What is set of natural numbers? Denoted by n. It is the set of counting numbers 1, 2, 3 and so on. Set of integers. Natural numbers, their negatives and 0 also. This set is the set of integers. Set of rational numbers. Numbers of the form P over Q, where P, Q are integers, Q is non-zero. This set is the set of rational numbers denoted by Q. Set of irrational numbers. Numbers which are not rational. All the numbers which cannot be written in the form P over Q for any integers P and Q. For example, square root 2, pi, e, these are irrational numbers. There is another difference between rational and irrationals. What is that? The decimal form of rational numbers either terminates or repeats. For example, 1 over 3 can be written as 0.333 and so on in decimal form. So here 3 repeats. Likewise, you can check for something like 1 over 7. Okay. In this case, some group of digits will repeat. So the decimal form of the rational number either repeats or terminates. Terminating case 1 over 2 is 0.5, here it terminates. But in case of a rational number, the decimal form neither terminates nor repeats. You can express root 2 in decimal form, pi, e, etc. These are irrational numbers. Set of real numbers carry rational as well as irrationals. Geometrically, you know, on the number line, integers are visible. Okay, fractions are here in between. This whole number line is fully packed with real numbers. We also call it real number line. Okay, next, axioms of real numbers. These axioms are important. You are using them unconsciously while doing calculation with the real numbers. But these are in fact axioms of real numbers. Means these are standard postulates about real numbers which are directly used. These are without proof. First is closure property of addition. What is that? If you choose any two real numbers A and B, their addition is again a real number. You know it. The set is closed with respect to addition. You are choosing two numbers from the set. Their addition again goes to the same set. So R is closed with respect to addition. Commutative property means you can commute two real numbers in addition, the result remains unchanged. A plus B and B plus A are same. Both are same. Both are equal. Associative property of addition. Association can be done in either way. Whether you first add B and C, then A, or you add A and B first, then C. You can do the association either way in addition. The result of both sides is same. Both are equal. So this is associative property of addition. Additive identity means, what is additive identity in real number? 0. Because if you add 0 to any real number, you get the same real number. So 0 is additive identity. Additive inverse. If A is any real number, then minus A is another real number. Addition of the two gives the additive identity. So minus A is additive inverse. So these 5 axioms are there with respect to addition. Likewise, there are further 5 axioms with respect to multiplication. You can see product of two real numbers is a real number, a into b equal to b into a, commutative property of multiplication. Then see associative property. What is multiplicative identity in real numbers? What is the real number that is multiplied to any real number and the real number remains same? 1. A into 1 is a for any real number a. So 1 is multiplicative identity. Multiplicative inverse. What should be multiplied to a to get the multiplicative, means to get the multiplicative identity 1? 1 over a. This doesn't hold in one particular case if a is 0, but for each non-zero real number, multiplicative inverse exists. Okay. Next, multiplication is distributive over addition. This is the 11th axiom about real numbers. What does it mean? A into b plus c equal to ab plus ac. Okay. This can also be written as b plus c into a. So multiplication is distributive over addition. You can open the bracket like this. Multiplication is distributing over b as well as c. You can see here. Okay, so distributive property holds. Here left and right distributive laws matter. Sometimes left distribution is allowed, right is not allowed. See this example. In real numbers, division is only right distributive over addition. See, you can write 2 plus 3 over 7 as 2 over 7 plus 3 over 7. But you cannot do the reverse. 7 over 2 plus 3 cannot be written as 7 over 2 plus 7 over 3. Correct? So division is distributing over right, over addition from the right side, but not from the left side. Okay, so hope you understand this point. Now, let's see what is a real vector space. This is the key definition in this chapter. You should understand this definition clearly so that you feel comfortable in doing problems on real vector spaces. Read it carefully. A non-empty set V is said to be a real vector space if two operations denoted by plus and dot are defined such that for all UVW belonging to V and AB belonging to R, following properties are satisfied. Before I tell you the properties, again see this statement. V is a non-empty set, plus and dot are two operations. With respect to those operations, following properties are satisfied. Okay. See what are the properties. First property, U, V, W are from V. First property is U plus V again belongs to V. What does it mean? V is closed with respect to addition. V is closed with respect to addition. Next, commutative property with respect to addition is satisfied. Next, associative property. Next, additive identity exists in V. Next, for each U belonging to V, there exists minus U belonging to V such that addition of the two gives the additive identity. It means for each U belonging to V, there exists additive inverse. So these 5 properties are satisfied with respect to plus, the first operation. Okay. Next, sixth property, A dot u belongs to V. Remember that A is a real number, u is a member of V. So A dot u belongs to V. A dot u plus V is A dot u plus A dot V. Seventh property. Now A and B are two real numbers, u belongs to the set V. A plus B dot u should be A dot u plus B dot u. Ninth property, AB dot u is A dot B dot u. 10th, 1 dot u is equal to u. Now it's very important. I will go to the properties again, but you should understand the meaning of plus and dot here. We call the members of V as vectors just to make a difference between the members of V and the members of R. We call the members of V as vectors while the operation plus is called vector addition. Okay? Plus that you are seeing here is vector addition. Between the members of V it is vector addition. But between the members of R, A and B are members of R means A and B are real numbers. So this plus is ordinary addition. This plus can have any definition depending on the given problem. You will see the examples. This plus and this plus are different, may be different. This plus is between two vectors. This plus is between two, see the next line, scalars. We are calling the members of R as scalars, while we call the operation dot as scalar multiplication. So A dot u, this dot is scalar multiplication, but here you are seeing A into B. This is ordinary multiplication between two real numbers. Okay, so this difference you should understand. A dot u belongs to V means A dot u is also a vector. We are calling members of V as vectors. So A dot u is a vector, A dot V is also a vector. This plus is the vector addition. It is not ordinary addition of real numbers. But here this is ordinary addition of real numbers. This is ordinary multiplication, but this dot will have some definition depending on the problem. So point is that, let's go back. V is a non-empty set. Two operations will be defined. These will be given to you to make it a vector space. Okay. So this operation you will call vector addition, dot you will call scalar multiplication. These will have some definitions. Okay. So depending on the given definition, you will use these operations. So with respect to plus, these 5 properties must be satisfied. And with respect to scalar multiplication involving this vector addition also, these 5 properties must be satisfied. Okay? You will see example, then you will understand it clearly. So there are 10 properties for V to be vector space, for V to be real vector space, because the scalars that you are using are real numbers. So keeping in mind these 10 properties, let us see the first example. Before example, some more properties are there. Using the properties of vector space, we can easily prove these 3 common properties in the vector space. What are these? A into 0 is always 0. This into is scalar multiplication. It is not ordinary dot of real number because 0 is a vector. Dot is the scalar multiplication defined in the vector space. A is a real number, 0 is a vector, A dot 0 is 0. This can be proved using the properties of vector space. Using the properties of vector space. See how can I prove it. I prove one property, remaining 2 you can see from the lecture notes. A dot 0 can be written as A dot 0 plus 0. This can be written as A dot 0 plus a dot 0 plus minus a dot 0. It is fine because addition of a vector with its additive inverse gives the additive entry. So it's fine. Now I can write it a dot 0 plus 0. You know this kind of property is there in the vector space. Which property? See this property, a dot u plus a dot v can be written as a dot u plus v. Property number 7 I am using here. Next, 0 plus 0 is again 0, 0 vector, because 0 is additive entity. But now, where we have reached, a vector with its inverse added gives you 0 vector. So, proof of these properties is simple. Others also you can see from the lecture notes. Main thing is that any scalar multiplied with 0 vector gives the 0 vector. Second, the real number 0, scalar multiplication with any vector gives the 0 vector. Minus 1 real number, scalar multiplication with any vector gives its additive inverse. This minus and this minus are entirely different. Maybe entirely different. Why? Because this is ordinary minus in real numbers, but this minus is indicating inverse of this vector, additive inverse of this vector. You will see that the vectors can be any type of members. These may not be real numbers. Okay. You can verify all properties in this set of the vector space. What is this set? The set V equal to 0 carrying only the real number 0 is a real vector space with respect to the addition and multiplication operations of real numbers. What does it mean? In all these properties, if I choose U0, V0, W0, A and B are any two real numbers, then you can check all these properties are satisfied. Okay, so it's a vector space. You can see it yourself. But let's see this problem. The set R of real numbers is a vector space with respect to the following operations. This is usual addition of real numbers. U plus V is simply addition of two real numbers. And A dot U is A times U. This is ordinary multiplication of real numbers. Because now your U and V, what is V here? Capital V. Capital V is R itself, the set of real numbers. Okay, so here scalars are real numbers, vectors are real numbers, operations are simply addition of real numbers, simply multiplication of real numbers. So naturally you can check all those 10 properties of vector space are satisfied. You can check yourself one by one. Why those properties are satisfied with these two operations? Because these properties are nothing but these are coming from the axioms of real numbers. From the axioms of real numbers, you can check all these 10 properties are satisfied when I am choosing vector addition as this and scalar multiplication simply ordinary multiplication of real numbers. Got it? Let's see a different example that will give you the idea of vectors. In fact, means how vectors can be different from scalars. Here, the set V is R2. R2 means R cross R. Means what kind of members are here? X1, X2 type members, where X1, X2 are real numbers. Okay. Means ordered pairs of real numbers are there in V. So here the vectors are ordered pairs. These are not simply this is not simply a single real number. It is an ordered pair that is a member of V. So what are the operations, the vector addition and scalar multiplication operations in this example? How to add two vectors x1, x2 and y1, y2, say are any two vectors in V, or in this case it is R2. Then how to add coordinate wise addition. This is definition. How to perform scalar multiplication. A is any real number, x1, x2 is a vector in R2. Then the scalar multiplication is to be performed using this. Simply multiply the real number A with each entry in the vector. Coordinate wise multiplication. So these are the definitions of vector addition and scalar multiplication that you will follow in verifying all the 10 properties. Definitions of the vector addition and scalar multiplication are very crucial. Focus on those for performing all the calculations. This is the key thing in a vector space. So here first thing, what kind of vectors are there? Ordered pairs. How to perform their vector addition? Coordinate wise. How to perform scalar multiplication with a real number? Multiply coordinate wise. These are the definitions. Now let us see the properties one by one. We need to prove R2 is a vector space over this set of real numbers. So let us choose three vectors UVW, but what kind of vectors are here? Ordered pairs, so you will choose x1, x2, y1, y2, z1, z2 as your UVW. These are members of V. A, B are any two real numbers. So what is the first property that you want to verify? Closure with respect to vector addition. So what is closure property? If you pick any two members from the set V, then their sum again goes to V. So let's solve U plus V. What are U and V in this case? x1, x2, y1, y2. Now here is the point, how to add these two? Coordinate wise by definition. So if I do coordinate wise addition, this is the output. Next, whether it belongs to R2, how to check it? Because closure property means the output goes to the given set V, in this case R2. x1, x2, y1, y2 are real numbers, their additions are again real numbers. So overall it is an ordered pair of real numbers, so it goes to R2. No doubt about it. So closure property is satisfied. Commutative property. First solve the left hand side, U plus V. You want to prove it, V plus U. So U plus V, already it is solved here. Output is this one. Now solve V plus U. If I solve V plus U, then I get this thing. But these two ordered pairs are equal. Why? Because x1 plus y1 is same as y1 plus x1. What are we using here indirectly? The commutative property of addition in real numbers. This is an axiom, okay, that you observed in the set of real numbers. So it's fine, both are equal. Similarly, these are equal. So you see, it's very easy. Just you go by the definition of vector addition in the vector space and keep on verifying the properties. Axioms of real numbers you can use directly. At the most you can mention here you are using closure property of vector addition of, no, not closure property here, commutative property of the vector addition in real numbers. So it is fine. You have verified U plus V equal to V plus U following the definition of vector addition in the given vector space. Third property associative, same way you can do. First solve U plus V plus W. Keep on solving, you get something. Keep on solving means you will follow the definition of vector addition each time wherever you need addition. Then solve right hand side. This is the result. Now these two should be equal. Why these are equal? Again you are using associative property of the addition in real numbers. These are equal. So associative property is satisfied. Next, identity, additive identity. So what is additive identity? For this means what should I add to this vector, or I am assuming it u. What should I add so that it remains same? 0, comma 0. You know, if I add coordinate y, it remains same. So 0, 0 is additive identity. You can add either way, result is same. Next, existence of inverse. So what do you think? What is the inverse of this? Minus x1 comma minus x2. You know, this is another ordered pair of real x1 x2 are real number. This is also real number. This belongs to R2. This will act as additive inverse because if I add these two, I get 0, 0. You can see here how to write it. So minus x1 minus x2 acts as additive inverse of x1 x2 in R2. Sixth property, scalar multiplication. A dot u. What is definition of scalar multiplication? Multiply the real number coordinate wise. Now this is ordinary multiplication. A is a real number, x1 x2 are real numbers. So this is again ordered pair of real numbers. Goes to R2. So sixth property of vector space is satisfied. Seventh, one scalar, two vectors. A dot u plus v. Solve it. First apply vector addition. You get this. Then use scalar multiplication definition. Multiply coordinate wise. This is the output. So this is the output of left hand side. A dot u plus v. Now solve right hand side. A dot u plus A dot v. You can see output is same in both the sides. So seventh property is satisfied. One scalar, two vectors. It's kind of left distributive now, isn't it? Dot is distributive over addition. But of course, numbers are different. This is a real number. These are vectors in R2. Next, two scalars, one vector. A plus b dot u should be equal to A dot u plus A dot b dot u. So solve first left hand side A plus b dot u. Go by definition. You get this. Then solve A dot u plus b dot u. Following the definitions of scalar multiplication and vector addition, you reach here. You can see both are same. So eighth property is also satisfied. Ninth, again two scalars, one vector, but this is kind of assertive line multiplication, not exactly, but you can remember it like that. AB into u should be A times BU. You can check here, following the definition of scalar multiplication, you can write it like this. Now solve the right hand side, A dot B dot u. Again go by definition of scalar multiplication. You reach here, you can see both these are same. So ninth property is also satisfied. Tenth property, 1 is a real number if I solve 1 dot u. Following the definition again of scalar multiplication, multiply coordinate wise, we get the same vector x1 x2. That means 10th property is also satisfied. So this is the way you can verify all the properties for proving a given set as vector space under the given operations. Every time I am repeating that step again because that is important. Every time I am following these two definitions, coordinate wise addition, coordinate wise scalar multiplication, in doing all the calculations while verifying the properties of the vector space. What is important? See the form of the vector. You have to use those kind of vector in place of UVW, and you need to notice very carefully how to add two vectors. Here it is coordinate wise addition. In some other problem it could be some other definition. You will see further in the examples. Same way, notice what is the exact definition of scalar multiplication. So while verifying all the properties of vector space, you need to follow the given definitions of vector addition and scalar multiplication. If you observe these three things carefully and remember the 10 properties of vector space, I think it's a very easy procedure. Okay. So one problem I have shown you all the steps. Now you can see further examples of vector spaces that you will do yourself. Some proofs are given in the lecture notes. You can see there. Here I explain the main things. What is this set? Mn. Collection of all matrices of order m cross n. In the matrices, all entries are real numbers. So Mn is the set of all m cross n matrices with real entries. This forms a vector space under these two operations of vector addition and scalar multiplication. So what is a vector addition? You can understand it is simply addition of two matrices. Ijth element of first matrix is added to the ijth element of the second matrix. This is ordinary multiplication in matrices. You can see this A is multiplied with each Aij entry of the matrix, isn't it? So this is usual addition of matrices of order m cross n. This is usual multiplication in matrices. Following these two definitions of matrices means vector addition and scalar multiplication, you can verify all the 10 properties of vector space. So it forms a vector space. So it's a standard example you should know. The collection of matrices forms a vector space with respect to ordinary addition of two matrices and ordinary multiplication by a scalar in the matrix. Okay. This is also a standard example. What is it? Pn is the collection of all polynomials of degree less than equal to n. N is a positive integer, non-negative integer. Okay. Pn is the collection of all polynomials of degree less than equal to n. So see what are the definitions of vector addition and scalar multiplication. In vector addition, what is done? The two polynomials are simply added. You can see here the coefficients are added for like powers of x. So it is simply addition of two polynomials. And scalar multiplication is each coefficient in the polynomial is multiplied by the real number a. So it is ordinary multiplication by a real number to all the coefficient in the polynomial. So under these two operations, it is very easy to verify that this set forms a vector space. So collection of all polynomials of degree less than equal to n forms a vector space with respect to these two operations. Next, phi is the collection of all functions defined on the interval 0, 1, closed interval 0, 1. It also forms a vector space under these two operations. First operation is ordinary addition of two functions. How you add two functions, okay, you know that. And second is ordinary multiplication. Multiply the function by the real number. So this is ordinary addition, this is ordinary multiplication. Ordinary word I am using in the sense that you are familiar with, okay. So it can be verified that it forms a vector space. But what about this set? Same collection, but now I have imposed one extra condition on each function in this collection. What is that condition? F of half should be 1. Now this set doesn't form a vector space. Can you tell me why? It doesn't form a vector space. Which property is not satisfied? Even if a single property is not satisfied, the set doesn't form a vector space. There are 10 properties you need to verify for a set to be vector space under the given operations. If you are able to find even a single property which is not satisfied, then it is not a vector space. You need not to verify the remaining 9. Okay, so which property is not satisfied here? Let us choose F and G, two members from this set phi. So if these are members of phi, this given collection, then f of half should be 1 and g of half should also be 1. Let us try to verify the closure property. If f plus z again goes to phi, then what should happen? Value of this at half should be 1. But what is it? It is f half plus z half. That means what? 1 plus 1? It is not 1. It means f plus z does not belong to phi. F plus z does not belong to phi. The given collection. Closure property is not satisfied, so it cannot be a vector space. This example is interesting because here the operations are unusual. We can call it unusual vector space. The operations are not ordinary here. You see, R plus is the set of positive real numbers. Vector addition is defined in this manner. In fact, vector addition is ordinary product of the two real numbers. U and V are positive real numbers, of course, here because the collection is of positive real numbers. So how vector addition is defined? Multiply the two positive real numbers and scalar multiplication. A dot u is u power a. Okay, so it's something unusual. Left side it looks like you are simply multiplying a with u, but the definition of dot, the scalar multiplication, says that how to operate it. Solve u raised to u power a. Okay. So in this case also you can verify all the properties. For example, first property, the closure property with respect to vector addition. U plus v is what? U into v. U and v are positive real numbers, so u into v is also a positive real number, right? So you can similarly you can verify all the remaining 9 properties. So main thing is that you need to focus on the definitions of vector addition and scalar multiplication. The solution of this example is given in the lecture notes. You can see how the different properties are verified using the definition of vector space. Okay. So do it yourself. Just follow these definitions of vector addition and scalar multiplication, then verify the 10 properties one by one. You will understand yourself how to do. Now look at this example. Show that the set R of real numbers is a vector space with respect to these two operations. What is first operation? U plus V, how to solve it? U, V are real numbers, it is given. U power 5 plus V power 5 and then whole power 1 by 5. What does it mean? Suppose I want to solve the vector addition of 1 and 2. What is the output from this definition? 1 power 5 plus 2 power 5 whole power 1 over 5. I have to solve this thing further. Okay. Likewise, if I want to solve 2 dot 3 here, let's see what is the meaning of dot here. Dot means a power 1 over 5 you need to multiply with the given vector. What are vectors here? Real numbers, and scalars are also real numbers, but the dot has a different definition. So let's say 2 is a real number and 3 is also a real number, but this is your v in this case. So what is it? By definition, it is 2 power 1 over 5 into 3. Now this into, or you can put the bracket in to avoid the confusion. You need to multiply these two things. There is no sign in between. So the right hand side is, it is ordinary multiplication. So you see the definitions here, these are also unusual. But under these definitions, you can verify all the 10 properties of vector space. Okay. First property, or you can say first condition given here means the definition of vector addition I keep as it is. Second, I change a dot u. I am saying a into u only. Now this is not a vector space. Can you think which property fails? This is an interesting problem. Which property fails out of the 10? Can you think about this property? There is a property in the vector space a plus b dot u should be equal to a dot u plus b dot u. What is left hand side by the given definition? Means I am solving this. By the given definition, a plus b is a real number. So according to this definition, it should be simply a plus b into u. Multiply a plus b is a real number, so multiply it with u. Okay, this is left hand side. Right hand side is a dot u plus b dot u. This is right hand side. Let us solve it and see what do we get. Following the definitions. What is a dot u? It is a u plus b dot u means bu. I have followed this definition, but for addition I have to follow this one, first one, because that I am keeping as it is. What it should be? Check it. What it should be? AU power 5, BU power 5, whole power 1 over 5. Do you think that this and this are same? No, these are not equal. U can take, U power 5 you can take out, but A power 5 plus B power 5 whole power 1 over 5 is not equal to A plus B. So you see this property is not satisfied. So you understand, if it is not a vector space, some or the other property fails. So main thing is that you need to keep in mind the 10 properties of vector space. After that, depending on the problem, you have one vector addition definition, another scalar multiplication definition. Following the two definitions, you need to verify the 10 properties one by one. Once you practice some problems, you will be very comfortable. It's a very easy concept. It's not difficult. But once you learn vector space, many other concepts are waiting for you, which are very beautiful to learn, and lot of applications are there. The vector space is having 10 properties. It is basically an algebraic structure with two operations, plus and dot. Okay. This plus can have any definition, dot can have any definition, v can have any type of members. So it is something general, okay. If you choose simply v equal to r plus dot, this is a vector space under usual addition and multiplication of real numbers, as you saw in some example earlier. So what are the vector spaces that you would like to collect in your mind at the beginning? The examples of vector spaces. The set of real numbers with respect to ordinary addition and ordinary multiplication forms a vector space. It's a real vector space. Then R2 is also a vector space. Which kind of members it carries? It carries ordered pairs of real numbers. But what is plus here? Coordinate-wise addition, coordinate-wise multiplication. In general, if you consider Rn, R3, R4, R5, etc., I am considering in general Rn. Which kind of entries are here? N tuples, points with n coordinates, where all xi's are real numbers. So here also I can consider the same operations. One member of Rn, another member of Rn, say y1, y2 and so on yn. So take coordinate wise addition. First operation, that is vector addition. Likewise, you can consider coordinate wise scalar multiplication. So this also forms a vector space. So Rn in general, where n is any positive integer, if we consider this operation as vector addition and coordinate wise scalar multiplication, then it forms a vector space. So it's a standard vector space, you need to remember it. Okay, you should remember it. Then matrices forms the set of matrices of order m cross n also forms vector space under usual addition of matrices and usual scalar multiplication in matrices. Collection of all polynomials of degree less than equal to n forms a vector space under usual addition of polynomials and usual scalar multiplication. The meaning of usual you understand, usual or ordinary, okay, that you are familiar with. After that I told you some unusual examples also, where plus can have any definition, dot can have any definition, it may or may not be vector space. Alright, so hope you understand the definition of vector space very well. Next time we will discuss subspaces, but before that you should be comfortable with the definition of vector space and some standard examples. Also practice the problems which are where the given set is not a vector space. So some or the other property of vector space fails, so you need to practice that kind of examples. Okay. Thank you. We will meet in the next lecture.